Hey, welcome back to your favorite Math 126 course. We're going to look at logarithmic functions today. So previously we looked at inverses, and we were working with things of the form y equals b to the x, such as y equals 2 to the x, right? Now, in order to find inverses of exponential functions, we're going to have to switch x and y. So in order to switch x and y for y equals 2 to the x, we'd just have x equals 2 to the y, correct? Well, this is where logarithms come into play, and there's two forms for logarithms. There's the exponential form, here's the exponential form, and then there's the logarithmic form of that same logarithm, which is 2 to the y equals x, y equals log base 2 of x. So there's two forms of this. If x equals b to the y, and I like to write that b to the y equals x, and then the logarithmic form will follow b to the y equals x, right? So there's two forms for exponential and logarithmic forms of this inverse of exponentials, okay? So this one here we have log base m of 5 equals 7. Again, I'm going to write it this way. I'm sorry, I wrote that wrong. Log base m of 5 is 7. So this is the log form. So the exponential form would be m to the 7 equals the 5. There's our exponential form. That's how I remember that, at least. Here's the next one. Here's the logarithmic form. So the exponential form of that logarithm would be c to the 8 equals the 6. Okay. So that's the property that these logarithms have. If log base b of x equals y, that's true if and only if b to the y equals x. Again, you can have those two forms. Okay, let's keep going here. This time it has the exponential form, and they want you to put it into the logarithmic form. So what I like to do is I like to write my log, and I go 1.4 to the 5th equals q, and that's how I remember that. Log base 1.4 of q equals 5. There's my logarithmic form. Same thing here, we have exponential form. I'm going to go ahead and write my log and my equals, and I'm going to go 2 to the d equals 8. So there's the logarithmic form. Log base 2 of 8 equals d. Let's do this one. X equals e to the y. So I'm going to go ahead and write my log, write my equal. And notice this is e to the y equals x, same thing. So e y equals x. There's the logarithmic form. Now this log base e, you should note, this log base e, that is a special logarithm, a log base e, and so they give it a special name. They call it the natural log of x. So log base e of x is the same as the natural log of x. These are the exact same thing. Again, natural log of x, natural logarithm of x is how you say that. So these are the same thing. Log base e and the ln of x are the exact same thing. Okay. Now we can also do logarithms on our calculators. Oh, there is another one I should also mention. That's another special logarithm, and that's log base 10 of x. That's called the common log. And the common logarithm, they often, if they don't write the base, these are the same thing. Log base 10 of x is log of x. So if they don't write the base, it's base 10. And your calculators, most basic scientific calculators, they can do log base e or the ln. They have that button on there, and they also have just a basic log button on there, which is log base 10, right? So they can do those two. So for example, if we're finding the value of log of 5, notice they don't write in any base, so you know this is base 10. And if we round that to the nearest thousandth, let's go ahead and pull up our Desmos. Desmos, let's go to our scientific calculator, and let's see, what were we punching in? Log base, log of 5. So I'm going to go with my functions. I'm going to punch in log. See the log? There's log base 10. And there's the natural log. That's log base e. All right. So we're going to do log base 10 of 5. Parenthesis. So 0.69897. And we're going to do that to the nearest thousandth. So it looks like the number to the right is a 9, so I'll bump that up. 0.699. Okay. Now this next one, let's do natural log of 7 now. So now let's go ln. So I hit that ln key right there. ln 7. Again, this is log base e, same thing. Enter. So 1.94591. And we're going to round this to the nearest hundredth, so that right there. So to that position, so I look to the right of the 4, I got the 5, so 5 will bump that up, so approximately 1.95 on that. And that's how we use our calculator with these logarithms. Okay. Now, if you remember the equal basis properties, if it is a to the u equals a to the v, then u has to equal v. And so we'll use that to help us solve something of the form log base 4 of 64. So what we'll do is we'll just set it equal to something. Let's go ahead and set it equal to like y or x or something. And now let's use the fact that we have this logarithmic form, but we can put it in the exponential form. So 4 to the y equals 64. And we're like, oh, 4 to the third must equal 64. In other words, y must equal 3. Therefore, log base 4 of 64 equals y, and y is 3. Right. So that's the value, the exact value of log base 4 of 64. Now I do realize some calculators will do a log base 4. We'll later in the course we'll actually give you a change of base formula as well, which is another way to do problems like this. Let's do this next one. Let's go ahead and set equal y again. So we have log of 1 over 10,000 equals y. And remember that the base is not shown, so it's base 10. And now let's put it in exponential form. So we're going to go 10 to the y equals 1 over 10,000. Let's go ahead and write that. Let's see, 10 to the 10,000, that'd be what? 10 to the negative 4. So I know y has to be negative 4. In other words, log base, therefore, log base 10 of 1 over 10,000 equals y, equals negative 4. All right, let's do a log of 0 on a calculator. In fact, let's go ahead and do this first by hand. Log of 0, let's say it equal to y. This is base 10, it's not shown, so it's base 10. So we go 10 to the y equals 0. So I think to myself, well, 10 to what equals 0? Well, there's no way you can do that, right? 10 to nothing. There's nothing, no value of y that will make this true. So this does not exist. In fact, you could put it in, let's go ahead and put it in into decimals, log of 0, and we'll show you. Let's see, find our log 0, and notice it says undefined, right? So again, that's undefined on a calculator. as well. Calculator smart enough to figure that out. So it does not exist, undefined. Now let's actually try and draw what the logarithmic function would look like. And you know what? I'm going to take. Let me take two functions. Let me do first y equals 2 to the x. Let me have that be my b, okay? We know y equals 2 to the x. If we were graphing that, 2 to the 0 is 1, 2 to the 1 is 2, 2 squared, plug 2 in is 4, 2 to the third, 8. Let me go to the left now. 2 to the negative 1 is a half, 2 to the negative 2, 1 over 2 squared, 2 to the negative 3, and so on. And so we get this function right here, goes through this 0, 1. It's got those points on there, right? And of course it had the horizontal asymptote y equals 0, right? So this is our function y equals 2 to the x. Well, its inverse would be where we switch x and y. So instead of y equals 2 to the x, it'd be x equals 2 to the y. In other words, let's do that in logarithmic form. 2 to the y equals x. So y equals log base 2 of x is the one that we'll graph now, and so that'll flip all those points around. So instead of 0, 1, we'll have 1, 0. Instead of 1, 2, we'll have 2, 1. Instead of 2, 4, we'll have 4, 2, and 8, 3, and so on. All these points flipped around. And that key point 0, 1 becomes that key point 1, 0. And we flip all those points around. Soon enough, we see this logarithmic function. So here is log base 2 of x. So log base 2 of x is the inverse of 2 to the x. And instead of a horizontal asymptote y equals 0, this one has a vertical asymptote of x equals 0, right? The black one had a range of 0 to infinity. Right? The black one had this range from 0 to infinity. So the domain on this vertical on the log base 2 of x, the domain would be 0 to infinity. In other words, 0 to infinity would be the domain on that, right? So all these x values got to be positive, right? Because we're not going to touch that vertical asymptote, okay? So, and similarly, you know, if you were to draw 3 to the x, then log base 3 of x would be its inverse. 3 to the x just a little bit steeper, and log base 3 of x, of course, would flip all those around. But let's go ahead and use this information to find the domain of natural log of 2x minus 7. So the natural log of 2x minus 7, let's think about the natural log for a minute. Here's y equals e to the x. Its inverse would be log base e of x. Well, we know that to be the natural log of x. Here's the natural log of x. So it looks a lot like those other two, just distance a little bit steeper, right? The e to the x a little steeper and so on. Natural log, but very similar. They go through 0, 1, and 1, 0. So we know the domain on this is x got to be positive. Well, this is not the natural log of x. It's the natural log of 2x minus 7. So we know that 2x minus 7 has to be positive. So that's how we can get our domain on this. So we can set that equal or greater than 0. Add 7, divide by positive 2, divide by positive 2. So we know the natural log of 2x minus 7 is going to be greater than 7 halves. Okay, so it's going to look, I don't know, something like this again. That's what we're concerned about. The domain takes off from 7 halves on. Okay. Now let's do this one. Log base 3 of 6 minus x. Okay, well, 3 to the x. Here's 3 to the x. And we know log base 3 of x looks kind of like this. Log base 3 of x, its inverse. And then we know x is positive, right? That x is positive. Well, we don't have log base 3 of x. We have log base 6 minus x. So we know 6 minus x has to be positive. Let's add x, so we have 6 greater than x. In other words, x has got to be less than 6. Now we didn't graph this, but you could take a look at the graph of the actual log base 3 of 6 minus x, and what you'll see is the domain is from negative infinity up to 6. Here's your domain on that. Now what about this one? Well, again, we know this has got to be positive. So we've got this rational portion. It's got to be positive. So we're going to have to find the critical points and test around it. All right. So the critical points come from the zeros or where it's undefined. So if 2 minus x equals 0. So add x, I get x equals 2. Over here, subtract 2, subtract 2. So negative 2 and 2 are going to be our testing intervals. And I don't want to have either one of those, because if I plug in negative 2, I'd have 0 being greater than 0. So I don't want to include that one. And then I don't want to include the 2 either, because that makes it undefined. So there's no way that's going to be a part of it either, right? Because we get this thing, that being undefined. So let's go ahead and test now. Let's test like negative 3 into this. So we got negative 3 plus 2 over 2 minus negative 3. So I got negative 1 over 5. Is that greater than 0? False. So that's not part of it. Let's test like x equals 0. So 0 plus 2 over 2 minus 0. So I have 2 over 2. That's true. So that's going to be part in my domain here. And now let's test something over here like 3. So 3 plus 2 over 2 minus 3. Is that greater than 0? Well, 5 over negative 1 is not greater. Negative 5 is not greater than 0. All right, so false. So it's the only part of my domain is from negative 2 to 2, not including the endpoints there. All right, let's go ahead and graph now some of these using transformations. So I'm thinking about this is log base 3 of x, okay? So here's log base 3 of x. It goes through 1, 0. I mean, you could plot some points if you wanted to. It goes through 1, 0. It also goes through 3, 1. You know, because I'll show you how you can check that. 3. If I plug 3 in for x, right? Let me write it this way. Log base 3 of 3 equals y. Then 3 to the y equals 3. Well, that's 3 to the 1, so y must be 1. Y must be 1. So 3, 1, and so on. You could pick some nice points, some other nice points to throw in, but you kind of get the idea. And this has that vertical asymptote x equals 0, right? That vertical asymptote x equals 0. So what this will do, right, we know that's going to move that horizontally to the right 4 units. So let's go ahead and move it to the right 4. So that means 1, 2, 3, 4. Our horizontal asymptote is going to be bumped to the right 4 units. And all those points are going to be the same. It's going to go through like that, right? So if you could, you know, if you wanted to plug a few points in, like 5, right? We'd have log 1, y equals log base 3, 5 minus 4, which is log base 3 of 1. So we know 3 to the y equals 1. In other words, 3 to the 0. So y is 0. Y is 0. So we got 5, 0 right there. Another nice point would be 7. Right, 7 would spit out that 1. Again, it's moving this one to the right 4. All right. All right, let's go ahead and let's do negative log base 2 of x plus 3. So this is log base 2 of x, so which has a point, you know, still goes through 1, 0. If you plug 2 in, you could solve that and you get 1. Still has that same vertical asymptote, right? The vertical asymptote is x equals 0. So the first thing we're going to do is we're going to number 1, we're going to reflect that about the x-axis. Okay, so now we've reflected about the x-axis, but now we're going to be going like this instead, right? And then number 2, right here, now it's going to be a horizontal shift to the left 3 units. So now that vertical asymptote goes left 1, 2, 3, but all those points are going to look similar. Right? Anyways, you could kind of plot some points on there, but our x-intercept will be right there. In fact, we could go ahead and check that. So -2, 0. So let's check it. So it should be y equals negative log 2. If I plug -2 in for x, negative log 2 of 1. And so log base 2 of 1 is 0. All right? In other words, 2 to the 1 would give you 2 to the y, right? Would give you that 1 there. So point correct. Now let's keep going. Now this is kind of in an awkward form, and frankly, we need to think about what does the natural log of x look like. Well, the natural log of x is the inverse of e to the x. So it's going to go through here, and then it's going to go through, this is e comma 1, right? 2.718 comma 1. All right, so here's the natural log of x. Same vertical asymptote, x equals 0. So it's going to be looking like that, except I got to get this in a form that I can actually work with. So let me write it this way. Negative x plus 1, but then let me take out a negative here, and you can see number 1, that's your first reflection on this thing. So it's going to go ahead and reflect it about the y-axis. And then, number 2, then it horizontally shifts it right 1 unit. Okay, so the whole thing shifted right. So it reflects it. Let's go ahead and do the reflection about the y-axis. So if I reflect it about the y-axis, instead of 1, 0, I have -1, 0. But it looks the same otherwise. So here it is. This would be the ln of -x. Okay, it reflects it about the y-axis. Now we're going to shift that to the right 1 unit. Okay, so right 1 unit, the whole thing. So if I shift it to the right, instead of a vertical asymptote at x equals 0, now the vertical asymptote is at x equals 1. Instead of -1, 0, I got 0, 0. And I could graph any other points if I needed to. But that's what we're going to look like, right? And our x-intercept is right there at -1, 0. So in other words, if you plugged in -1, I'm sorry, I wrote that wrong, into the original 1 minus x, or you could put it into the one manipulated same form of that. If you put in -1, I'm sorry, what am I doing? Oh, that's 0, 0. I labeled that wrong. My apologies. There's my axes right there. Good grief. So I'm throwing in 0. Sorry about that. Again, I labeled that wrong right there. That's 0, 0. So we got the natural log of 1. The natural log of 1 is 0. So There's your x-intercept. All right, this one, notice we have no base. So this is base 10. I'm comparing it to the parent function base 10, which will go through 1, 0. And then the next one it'll go through is actually 10, 1. And vertical asymptote x equals 0. So let's do number 1. Let's go ahead and reflect it about the x-axis. So then we would look like that. All right. Number 2. Now I'm going to reflect it about the y-axis, the negative on the inside there. Okay, there's the reflection about the y-axis. And then lastly, that plus 2 in there, that is a horizontal shift left 2. So the whole thing goes left 2, 1, 2. All right, so from negative 1, 0 to the left 2. From x being 0 to x being negative 2 would be the vertical asymptote, and then everything else looks the same. And there's our function. And our x-intercept right there at, say, is a 1, 2, 3, negative 3, 0. Negative 3, 0. So in other words, if you plug that in, negative 3 plus 2, I get negative 1. Well, negative 1 is 1, and log of 1 is 0. So we get 0. So negative 3 comma 0 for that. All right, let's go ahead and solve some logarithmic equations now by changing it into exponential form. So we're going to use that property, if log base b of x equals y, then b to the y equals x. So 5 to the third equals x. So 5 times 5 times 5, 125 is x. There's our answer. Let's do this next one similarly. So x to the third equals 1/8. Right? X to the third is 1/8. So now we'll just solve for x. Let's go ahead and take the third root on both sides. So we have x, third root of x cubed is x. Third root of 1 is 1. Third root of 8 is 2. So we got x equaling 1/2 on that. Let's do this next one here. We got log base 4 of x squared plus 9. Let's use that property. So 4 to the 2 equals x squared plus 9. So 16 equals x squared plus 9. Go ahead, subtract 9 both sides. So 7 equals x squared. Squared equals 7. Now we'll square root both sides. So we got plus or minus root 7 on that. Five to the 2, right? 5 to the 2 equals 4x plus 5. So we get 25 equals 4x plus 5. Subtract 5 on both sides and divide by 4. So we got x being 5 on that. This next one, we're going to take 1/2 to the third. All to the third equals that 3x minus 7. Well, 1 to the third is 1. 2 to the third is 8. Add 7 both sides. So I got 3x equals 7 and an 8. Let's see, 7 and 1/8 gives me 57 over 8. And then lastly, we'll divide by 3 on both sides. So x ends up being 57 over 24. All right, last one here. Notice it's in exponential form right now. So what I'm going to do is I'm going to go ahead and write the log, and I'm going to go e to the x plus 5 is 4. So I got log base e. Now remember, log base e is that natural log. All right, that's log base e. We call that the natural log. They're the same thing. Equals x plus 5. So natural log of 4, that's just a number. You could punch it into your calculator. So we're just solving this thing for x. So x ends up being a natural log of 4, some number, minus 5. That's it. Thank you so much for watching. That's a little introduction to logarithmic functions. See you guys next time.